In this video, we're going to take a look at some properties of radicals that'll help us simplify radical expressions and work with them in various ways as we move forward. So we'll go ahead and just start with the properties that we need to know, get comfortable with at this point in time. So for all four of these properties, two of them we've seen already, but they're so important they're worth mentioning again. We need to keep in mind that the nth root of A and the nth root of B will be real numbers. What that's basically saying is if n is even, then A and B are positive numbers. Because as we talked about earlier, if n is even and these are negative numbers, then that does not represent a real number. It represents something else that we'll talk about a little bit later. So in this first property, I just call it property 1, not that it matters. We just need to understand and be able to use the property. If you have the nth root of two numbers being multiplied, so your radicand consists of a product, of two things being multiplied. It turns out it's perfectly legal to separate those into two separate radicals. So if you have the nth root of A times B, you can write that as the nth root of A times the nth root of B. It's going to be very, very handy. If you have the nth root of a fraction, or of two things being divided, turns out you can separate those into two separate nth roots. So the nth root of A divided by B is the same thing as the nth root of A as its own thing divided by the nth root of B as its own thing. And keep in mind, both of these properties, they work the other direction also. So if you have two radicals with the same index being multiplied, you can write those as one radical and you just multiply their radicands. Or if you have two nth roots being divided, you can write that as one big nth root where you divide the radicands. Now notice the index has to be the same for all of them. And then I went ahead and threw in two of our properties that we talked about in the earlier, and because they're so important. So if you have the nth root of a number to the nth, if n is odd, then it just simplifies down to the base of the exponent. If n is even, it simplifies to the absolute value of the base of that exponent. So we talked about those earlier, but I went ahead and mentioned them again because we're going to use them again. Now keep in mind, over here on the right side, in red, I've pointed out two things that students commonly think are true, but are not actually true, and you should never use. So if you have the nth root of two things being added or subtracted, it is not always true that you can just add or subtract those nth roots separately. So if you have the nth root of two things being added, you cannot split it up into two separate nth roots being added. Or if they're being subtracted, same thing. You cannot split them up into two nth roots being subtracted. So do not make that mistake. If you make it once, that's fine. You'll get dinged for it. Don't make it again. All right, so how are these properties useful? Well, let's look at this first example here. We have the square root of 98. So even though we don't put the little 2 usually, I'll go ahead and put it just to remind us it's a square root. Well, 98 is not a perfect square. There is no one number that when you square it, you get 98. However, it is true that 98 is the same thing as 2 times 49, and 49 is the same thing as 7 squared. So why did I do that? Well, I did that for a couple reasons. So let's look and see why. First off, I just wrote 98 as two things being multiplied. So I'm going to be able to split those up into two separate radicals. Not only that, I just rewrote it so that I had the same index and exponent on my radicand. So look, I can split this up into the square root of 2 times the square root of 7 squared. And I have the square root of 7 squared. See how they're both even. So that'll end up being the square root of 2 times the absolute value of 7. Well, the absolute value of 7 is just 7, so I end up with 7 times the square root of 2. Now I can't simplify that anymore because 2 is prime. So 2, I can't rewrite 2 into anything else other than 2 times 1. So I'm not going to be able to rewrite 2 so that I can use any of those properties, namely the one where the index and the exponent are the same, allowing you to get rid of the radical sign. I can't do that with 2 because 2 is prime. So basically, the way I've always thought about this is I'm always trying to rewrite my radicand so that I get exponents that match the index. So if the exponent matches if I can rewrite the number so that I get an exponent that matches the index, then that number gets to come out of the radical sign, like it did here. See how 7's not in the radical sign? So let's try another one. So I've got the cube root of 25 times the cube root of 10. So I have two cube roots being multiplied. So if you multiply, that's our very first property. If you have two nth roots, they have to have the same index being multiplied, you can write that as one nth root. So the cube root of 25 times the cube root of 10 would be the cube root of 250. Well, 250 is not what we call a perfect cube. There is no one number that when you cube it gives you 250. But maybe I can rewrite 250 the same way I wrote 98, where I split it up into smaller numbers. So what we can do here is earlier this year we talked about prime factorization, where you take a number and you write it, you keep breaking it down until it's only prime numbers. So one option you have here is to say, okay, 250 is 2 times 125. Well, 125 is 5 times 25, and 25 is 5 times 5. So if you look, I've got 2 times 5 cubed. Now, why is that important? Because 5 cubed, the exponent is 3, and my index is 3. So that's what I want to have happen. I want the exponent and the index to match. So I can write this as the cube root of 2 times 5 cubed, and then I can split that apart into separate radicals. And 2 is prime. I can't break 2 down anymore, so I can't get 2 to have an exponent of 3, so there's nothing I can do there. But I have the cube root of 5 cubed, and using our property, that should just end up being 5. So I have the cube root of 2 times 5, so I end up with 5 times the cube root of 2. Let's go ahead and take a look at a couple more. So for this first one, we have the cube root of 81 divided by 8. And 81 divided by 8, that's not a perfect cube. There is no number cubed that's 81. So what we can do is split this apart using one of our properties and do it as the cube root of 81 divided by the cube root of 8. So that's one of our properties. Go back and remind us. So the nth root of a fraction, you can split that up into two separate nth roots. So we'll split up into two cube roots. And let's see if we can't work with them separately. So 81 is not a perfect cube. So we can do the prime factorization and see if we can get some cubes out of it. So 81 is 3 times 27, which is 3 times 3 times 9. And that would be 3 times 3 times 3 times 3. Well, it's a cube root. So I want to put 3 of those together and write this as 3 times 3 cubed, because we need something cubed so that this thing will simplify. So we're going to replace 81 with 3 times 3 cubed, and then 8 is a perfect cube, so that would be the same thing as 2 cubed. So on the top, I've got 2 things being multiplied, so I'm going to separate those. That'd be the cube root of 3 times the cube root of 3 cubed. And then on the bottom, we're going to use our properties. Notice the index and the exponent are exactly the same thing. They're odd, so it should just come out to be 2. And then the numerator, on this one right here, I have the cube root of 3 cubed. So the index and the exponent are the same. They're odd, so that should just simplify to 3. So this ends up being the cube root of 3 times 3, all divided by 2, which we would probably typically write that, we'd put the 3 out front. So it'd be 3 times the cube root of 3, all divided by 2. Well, on B, we've got 2 square roots being divided. Now, the reason we have this one in here is notice that 60 and 5 will actually go into 60 evenly. So it'd be in our best interest to go ahead and write this back as one fraction. So we have 2 square roots being divided. You can write that as one big square root, and you just divide the radicands. And the reason we want to do that is because 60 divided by 5 actually goes into 60 evenly, goes in there 12 times. So 60 divided by 5 just simplifies to 12. And the square root of 12 will be fairly easy to simplify. So again, to simplify the square root of 12, you can just do the prime factorization. So that'd be 2 times 6, which is 2 times 2 times 3. So notice that would be 2 squared times 3. And that's useful because we want something squared since this is a square root. So 12 would be the same thing as 2 squared times 3, which I can then separate into 2 separate radicals. And the square root of 2 squared, since it's even, I end up with the absolute value of 2 times the square root of 3. And then we simplify that and get 2 square root 3. All right, so now let's do some variables, make it a little bit more complicated. So let's do this first one. I have 2 times a squared times b. Well, 2 is prime. I can't simplify that anymore. A squared, that's a good thing because I do have an index. Remember, my index is 2, even though we don't usually write it. So the fact that it's a squared is a good thing because I'll be able to simplify that. But it's b to the first, so I'm not going to be able to do anything with that because it's just b to the first. There's nothing I can do to simplify it. But what we can do is notice I have 3 things being multiplied. So I could separate this as the square root of 2 times the square root of a squared times the square root of b. Well, the square root of 2 doesn't simplify, but the square root of a squared, it does. Because remember, my index is 2, even though we don't write it, and it's even, so I end up with the square root of 2 times the absolute value of a times the square root of b. Well, the square root of b doesn't simplify anymore because it's just b. There's nothing else I could do with it. So what we're going to do is a little bit of rearranging. This would be the absolute value of a times the square root of 2 times the square root of b. Well, there's nothing else really to simplify. So what we would do is multiply those 2 square roots back together and just get 2b under 1 square root sign. Just looks better to have 1 square root sign than 2 separate ones. All right, let's try that again with this one. 36w cubed. So let's see if we can't simplify that. 36 is a perfect square. That's 6 squared. And then w cubed, I have 3 w's. So I can write that as w squared times w. And the reason I would want to do that is that gets me an exponent of 2 that would now match my index. So I can separate these square roots, and then use my property that says if the index and the exponent match and it's even, you get the absolute value of the base. And then the absolute value of 6 is 6. And then the absolute value of w, well, we'll just leave that w. And then the square root of w doesn't simplify anymore. Now, the reason we have this one in here is this is where things can get a little complicated because we're using these properties and we're practicing with these properties, but we do have this very subtle behind the scenes thing going on that we don't think about with all of these problems, but we do need to think about with this one. I don't know what W is. W is a variable. So W could technically be anything. It could be a positive number, a negative number, it could be 0, it could be anything. Well, turns out we actually have to think about it for a second. The square root of W, well, to do a square root, W has to be positive. That's the only way we're going to end up with a real number. And that's all we're talking about right now are real numbers. In a little bit, we're going to talk about another kind of number, but we haven't got there yet. For now, we're just talking about real numbers. So for this to be a real number, W has to be positive. Well, if W is positive, then there's no need for the absolute value, because if W is positive, putting absolute value on it doesn't do a thing. It's already positive, so the absolute value isn't changing anything. Okay, so we actually don't need the absolute value on this W. And the reason being is that W must be, it could be equal to 0 also. That wouldn't be a problem, but it just can't be negative. So W has to be greater than or equal to 0 in order for the square root of W to be a real number. Well, since W needs to be greater than or equal to 0 for the square root of W to be a real number, then we don't need the absolute value on that particular W. Now, if you go back and look at the one above, we didn't have to worry about that. So in my answer, I have the absolute value of A. Well, A doesn't show up under a square root sign anywhere. So A could be negative, it could be positive, it could be 0. We don't know what A could be, so I need to leave the absolute value on it because I don't know what A could be, and there's nothing that's making it so that A has to be a certain type of number. And then B, there's no absolute value of B anywhere. So B, since it's under the square root sign, B really should be a positive number or equal to 0, or else we won't have a real number. But as far as our answer goes, we don't have to adjust our answer at all. But on this one, since W shows up under a square root and it shows up in an absolute value, well, we can actually drop the absolute value because we need W to be positive or equal to 0 in order to get a real number, which means we don't need the absolute value on it since W isn't negative anyway. So we'll talk about this each and every time it comes up so you guys get the hang of it because it can be a little complicated to think about. All right, let's look at this next one. Notice we have two things being added under the square root sign. So as I mentioned earlier, you cannot split those up into two separate square roots being added together. But what I can do is notice how they both have a 4, so I can factor a 4 out. And then I can separate the 4 and the a squared plus b squared. That is legal because it's 4 times a squared plus b squared. And the square root of 4, that would be 2 squared. And the square root of 2 squared, since the index and the exponent are the same and it's even, you get the absolute value of 2. which is just 2. And that's as far as that simplifies. There's nothing else we can simplify. I am not allowed to split up a squared and b squared into 2 separate radicals. That is not a valid property. All right, well, the only other thing we want to talk about in this section is how to rationalize the denominator. So rationalizing the denominator is the process by which we get rid of a radical from a denominator. So it turns out we're not allowed to leave a radical in a denominator. If you're curious why, it's because for the majority of our history, there were no calculators or computers. So you had to do all your arithmetic by hand, and it was difficult to divide by a radical. So if you just got rid of the radical in your denominator, then you never had to divide by a radical. It just made your arithmetic easier. Well, that idea of getting rid of a radical in the denominator still is commonplace today, even though we have computers and calculators. So we still want to get rid of a radical in a denominator. So the square root of 5/3 is the square root of 5 divided by the square root of 3. Now 5 and 3 are prime. I can't break those up into anything. I can't simplify them in any way, shape, or form. But I have a square root in a denominator, and we're not allowed to have that. It's not simplified if we have it. I mean, it's okay to be down there. It's just not simplified, and we always simplify our expressions. So what we do to get rid of that is we multiply by 1. You're thinking, well, okay, if I multiply that by 1, it doesn't do anything. Well, turns out, multiply by 1, but we're going to multiply by a very specific 1. We're going to multiply the top and bottom by the square root of 3. So watch what happens. When I do the top times the square root of 3, I get the square root of 15. On the bottom, I get the square root of 3 squared. So I get square root of 15, and the square root of 3 squared is the absolute value of 3, which is just positive 3. So now I do not have a radical in the denominator. So this is now simplified. And I know what you're thinking, the square root of 5/3 and the square root of 15 over 3, it doesn't look simplified. But the whole idea is you now are dividing by 3 instead of the square root of 3. And that division is much easier to do. That arithmetic is much easier to do. All right, well, what if you don't have a square root in the bottom? All right, you just kind of use the same basic idea and just make sure that your exponent ends up matching your index. So to simplify this, we're just going to take the fraction, which has a cube root of c in the denominator. We're going to multiply by 1, but we're going to have that 1 be something very specific. We're actually going to multiply by the cube root of c squared. Now we got to multiply the top and bottom by the same thing. That way it's actually 1. And you think, well, how did I know to do that? Well, you'll see here in a second. If I do the top, I get 4 times the cube root of c squared. On the bottom, the cube root of c times the cube root of c squared is the cube root of c to the third. That's why I chose the cube root of c squared. So then when I multiplied by this one, I got an index and an exponent of 3. So I get 4 times the cube root of c squared, and the cube root of c cubed is c. And now there's no cube root in the denominator.